All right, so now we're going to talk about airframe fire protection systems. Now, there are a bunch of different types of these systems that are out there, both fire detection and fire suppression systems. Some aircraft have none of it, period. Some of it have just the detection systems, and then some of it have both detection and suppression systems. And the suppression systems vary widely, just like the detection systems vary widely. So this in particular section is something that it's important to learn, something that you're going to, if you're doing pre-flight, you're going to be testing these systems on a regular basis. You'll troubleshoot these systems, and it almost guarantee you'll have one of these systems on your oral and practical exam. So it's good to know them well because it's something you're going to see on a regular basis. Okay, so in order to get us started on fire, let's just study fire itself. Now, fire is a lot more complex than a lot of people give it credit for. There's different ways that fire will behave depending on what the fuel is, during what the conditions are, and everything. So, in order to make it a little bit more digestible to the student, the fire has been broken down into 5 different classes: A, B, C, D, and K. All right. Now, those types of fires will then also correspond, if you remember from general, they will also correspond with the different types of fire extinguishers. So, certain fire extinguishers are made to put out only Class A or Class B fires, and then some fires are only made for Class D fire, or fire extinguishers are only made for Class D fires, so on and so forth. So let's just kind of go through these classes and kind of get it right in our mind about the different types of fires and then where we could potentially see them on aircraft. So Class A fires are the most common. Whenever you think about your fireplace or burning brush or something like that, they're going to be Class A fires, just ordinary combustibles, wood, paper, cloth, things that you would think about burning, like that you wouldn't, like concrete burning is something that's kind of odd. It can happen, but it's not kind of the first thing that pops into your brain whenever it's burning. But Class A fires are those types of materials that will burn quickly and easily and are the most common to burn. So that's a Class A fire. Now, Class B fire is a flammable liquid. So, Class A fires, we can easily see them on the airplane. The interior could burn. There's tons of paperwork, so on and so forth. Class B fires are another one that's really easy. There's nothing but grease, oil, paint, and solvents throughout that entire airplane. Now, a lot of those liquids have been engineered to prevent them from catching on fire and sustaining a fire, but they can still do it under the right conditions with the right heat and so on and so forth. Not to mention that there's fuel on board the airplane. 100 low lead burns a lot easier than say Jet A, but either one will burn, and so that's something that you need to keep in mind. All right, so then you have Class C fires or live electrical equipment. Now, this is another one we're going to go over when we start talking about fire zones. Live electrical equipment burns pretty easily, mainly because of the heat that it generates. Once you get enough heat, eventually you get to the flash point of any material that's out there, and electricity is a really good way to heat things up. And we have electric heaters for a reason, and so those will be Class C fires. And you can find those anywhere that wires and switches and whatnot are found. Anywhere that electricity is going through, Class C fires are possible. All right, so Class D fires. This is where things get a little bit more exotic. Combustible metals. So notice that magnesium, aluminum, so on and so forth. Now, aluminum will burn, and we're going to show some pictures of some aircraft that have burned. And then you'll notice that the aluminum panels on the airplane have been burned up. Most aircraft crashes you'll find, they're just a big black pile of soot. There's you can't even really distinguish the metal in there at all, and that's because the aluminum burns. Magnesium is very popular in like helicopter transmissions and a bunch of other different parts of engines, specifically turbo engines. They'll burn up like no big deal. Like I remember in high school we had to burn a bit of magnesium. Burns very very hot, very very bright, very big white flame comes off of it. It's almost blinding. And matter of fact, I believe that they use those in flares too, and definitely in some fireworks and things like that for that reason. So magnesium will absolutely burn, and it's absolutely found in uh, the in the aircraft anywhere. Lastly, you have K fire. So you have like commercial cooking equipment, cooking oils, animal fats, vegetable oils. Now, you're probably not going to see a whole lot of that on aircraft. However, it's possible, especially when you start looking at like cargo holds, that we can control a lot about what goes on and off the aircraft. But at the end of the day, if somebody is trying to sneak something on board that they're probably not supposed to be flying, um, they're usually going to put more thought into it than you're going to put thought into trying to make sure that they're not doing that. And so you could get one of these types of fires that kick off, and you might need you might be confronted with a K fire. Anyways, so those are the classes of fires. Let's talk about fire zones now, where they could potentially catch on fire on an airplane. All right, the most obvious zone of an aircraft that you're going to see a fire is the engine. Why? Because that's where the fire is at. A engine is nothing more than a controlled explosion happening either over and over again if it's a reciprocating engine, or continuously if it's a turbo fan jet whatever engine. Now, if something happens with that engine that gets a little out of order, you could easily have a fire. If you have a compressor stall or a uncontained what do they call those? The engine comes apart. You're easily going to get a fire. You have all kinds of fuel pumps that are pushing fuel to that engine so that way it can continually run. And then if it doesn't contain the ignition of the engine, it's going to light that fuel off, and that fuel's just going to go all over the place. Not to mention that there's other things beside fuel that could catch on fire. For a long time, hydraulic fluid was another one that was really flammable. Luckily, now we've got that pretty well taken care of, but it still could potentially catch on fire and not be the prettiest day. But aircraft engines are obviously a place that we're going to spend a lot of time checking for our fire detection equipment and our fire suppression equipment and make sure it works. Okay, so another one is the APU. We haven't really talked a whole lot about the APU yet, but that's the auxiliary power unit. Essentially, the APU provides bleed air and electrical power and hydraulic power, depending on the airframe and the the configuration that airplane's in. That's what the APU does. Well, the APU is nothing more than a big jet engine in the tail that has all the same complexities and parts and pieces that your main engines have, and so they are just susceptible to catching on fire as your main engines. Okay, so cargo holds are another one that we need to be really wary of. Like I said before, you can't control what people put on the plane. You can try to intercept it and catch it beforehand. And so if they're trying to sneak something weird on that's not supposed to be there, they could potentially catch on fire if it comes into contact with something else or gets too hot or whatever. It can happen. So there's a flight in Hong Kong right here that's exactly what happened. There for a while, lithium-ion batteries were the number one suspect for a lot of aircraft fires because they would put them inside their baggage compartment and it would catch on fire whenever they loaded it on the plane. Now, there's all kinds of things that use lithium-ion batteries, especially now. Like all of the electronics that are out there, lithium-ion is generally light and small, so it works really well in primarily cell phones, laptops, you name it. Now, our electrolyte in there is highly flammable. It's an organic electrolyte, but it can catch on fire really easily. So what will end up happening is that one of those lithium-ion batteries will take a blow to it. It'll get punctured or dented or bent or whatever, and then that electrolyte will just go buck wild and start causing it to get really hot. As it gets hot, it'll hit thermal runaway, and then once you're in thermal runaway, it's just a matter of time for it starts to cause a flame. It lets off toxic fumes and smoke, and so the immediate reaction was just like, don't put anything that has like lithium-ion batteries in your luggage. And largely things are still that way, but the battery technology has progressed to where they're not nearly as dangerous. But this could be a type of fire that you run across, that somebody puts something that they're not supposed to in there, or something just catches on fire. When you start looking at like cargo operations, there's all kinds of hazardous material that gets shipped, and even though you might have two inert objects that are they're fine by themselves, when you put them together they cause a reaction. that create a fire. So it's really important to make sure that the all the paperwork and all the cargo actually matches the paperwork, and it's also kept together in a nice, clean, tidy way. Okay, so another place that you could get a fire is inside of a lavatory. Now, in your heavy commercial aircraft, you're going to have multiple labs, and they're usually one on the very front, one on the very back. Depending on the model of the aircraft, you could even have more. Triple sevens, A380s, 747s. They have labs all throughout the plane. Now, the challenge with that is that you have people that are going in there and doing all manner of things. And for a long time, people would want to smoke in the lab, and then they would, put their fire or put their cigarette out in the trash can. Trash can catch on fire, and then boom. That's why now, whenever you fly, they will talk about don't mess with the smoke detectors. It's against federal law and all that good jazz. Because there's people that have died because people smoked in the lab, and so we want to make sure that that doesn't happen. Once the fire gets going, it's going to be very, very difficult to stop, especially inside of the cabin where there's not a lot of fire suppression devices, if any at all. And so labs are a place where you will consistently see fires, even without the threat of smoking, because you have organic materials that are getting in there. You can have off gassing from that organic material as it starts to break down, and boom, you get like all kinds of spontaneous combustion. It's not as common as it used to be. We definitely have come a long way on this front, but it still could potentially happen. So that's something you need to keep in mind. Okay, so any sort of electrical bay is susceptible to fire. This is from the 787 Dreamliner, where they had a lithium-ion battery for the first time. They put it on the ground, and next thing you know, like boom, it catches on fire. There's a lot of battery technology that just hadn't really quite been developed yet. This isn't something that was known that could happen, and so anytime you do something new, you learn something. And one of the lessons from the 87 was that, hey, look, if we don't treat these batteries exactly right, they could potentially catch on fire. Now, out of all the different types of aircraft fire, this is the one that I've actually seen the most of for sure. Is that somebody won't, the one fire that always comes to mind was on a KC-46. The guy didn't tighten down power feeders. They were right about the same place in the on the ERAC, as a center line of one of the big power feeders to come off the battery, and the two that come in off the engine. He didn't tighten them all the way down. He didn't torque them correctly. That caused the lead to sit cockeyed and not fully connect or fully touch the rest of the post. Well, whenever you do that, when you reduce the surface area of one of those leads, you effectively, it's almost like you've installed a lighter gauge wire. Well, what happens with lighter gauge wires? The electricity still has to pass through there, so the amperage comes up. Whenever the amperage comes up, in those little spots where it's barely touching, it gets really really hot. You just think about the electrons are just making all that kind of friction as it comes through there. Boom, it catches on fire because of the heat, and then now you have this cascading effect where anything that's flammable around there. And keep in mind, a lot of this stuff is not necessarily built to be not flammable. It's you're not supposed to have fire around where, like, say, the peanut butter tape is on those connectors or whatever. And so it starts to catch on fire and starts to build, and then like fire can double itself. It's like every 30 seconds. If you have the right amount of oxygen fuel available to it, and so it just starts doubling and doubling and bigger and bigger and bigger. Next thing you know, the whole airplane's lost. And so this is something you always want to make sure that you follow your maintenance manual inside of the eBay particularly, and be very very sensitive to any sort of FOD that's in there, any sort of anything that could potentially lead it to be conductive and allow something to get shorted out, could potentially lead to an aircraft fire. And so we definitely don't want to have that, because this is a place that, like, it's right in the middle of the aircraft, right behind the pilots, and so you're going to end up having this massive fireball like right there, and you're going to start losing the aircraft systems quickly. You're going to have a lot of people trapped, and it could be pretty catastrophic if left unchecked. Okay, so wheels and wheel wells, very common to have aircraft fires for a couple of reasons. One, those wheels are going to be landing on surfaces that just are not as well controlled and well maintained as many others, to include inside the aircraft. So you have the possibility for all kinds of different debris and gunk and grime to either be combustible or to get up there and damage something on the aircraft that could lead to a combustible type situation. Then the other aspect of it is that you have an immense amount of heat on those aircraft brakes. You notice that you have a fire coming up between two aircraft right here on what I believe is a C5 and maybe a C-17, and so uh, that fire is going to be started because of the aircraft brakes. They simply just get too hot, some debris gets in there, it lights off. Once you get a fire going enough, it'll jump to the tire, and now you have a tire on fire, and then those tires will burn pretty hot. And you have a lot of tire that's right there next to them. So once it gets going, it's just going to keep on going, and you're going to end up having a problem really, really quickly. So that's something to keep in mind that you could potentially have fires inside of the wheel well. Okay, and then lastly, and probably one of the most unique ones to aviation is bleed air. Now, bleed air is essentially like you're taking a hot air away from the engine and using it for other things on board somewhere on the aircraft. Now, I remember whenever I did my private pilot training back in 2005, I remember reading a statistic that said that like 70% of all aircraft fires were generated by bleed air, and I have not been able to verify that statistic. However, the whether or not those numbers are right or not, the principle of it is absolutely true. Bleed air is you're sending extremely hot air into the aircraft, and if you have a leak somewhere, it's going to be blowing that hot air on any number of things. And keep in mind that the only thing that's really stopping everything from just catching on fire is the temperature that it's at. Once it hits to a flash point, it's going to start to catch on fire. And so if you have air that's hot, let's say if you have bleed air that's burning at 500 degrees Celsius, and the flash point of this combustible material is like 125 degrees Celsius. That material is basically inert most cases, but whenever bleed air gets exposed to it, now it's like basically going to catch on fire. It's well above its flash point. So if you have a bleed air leak somewhere on that airplane, there's a good chance that it could potentially cause a fire. And so in the picture here, the guy's demonstrating trying to find a bleed air leak with an ultrasonic imager. We're going to teach you how to do that. But just know that like you need to be really really careful working with bleed air, because if you were to crack a line, cause a problem or whatever, it could potentially lead to a catastrophic event. So now that we know something a little bit about the types of fires that could happen on aircraft and the different fire zones, let's talk about another killer that is not really as talked about it as fire itself, but something that you're going to have to prep for. Anytime you do an aircraft annual, you're going to change out a carbon monoxide filter or detector, and it's something that absolutely can kill people on a regular basis because it's very hard to detect without some sort of indicator inside the cockpit. Okay, so let's talk about carbon monoxide poisoning. So, what is carbon monoxide? So, whenever you have any sort of combustion, what will end up happening is that not all of the materials inside of the fuel are going to fully combust. And whenever that happens, the excess material will be discarded from the fire in the form of soot or smoke or whatever. One of those materials that all it comes from a fire that is not fully combusted is carbon monoxide, and it's actually flammable. Which when you get into a fire zone, this is really interesting. That the fire is just more or less a chemical reaction, and there's too much carbon monoxide being generated, so it doesn't fully burn all of that carbon monoxide. So that carbon monoxide gets expelled in the form of smoke, or in certain cases it just gets expelled. It's just gas, and it's clearer, it's tasteless, it doesn't smell. It's very much a silent killer because you could be carbon monoxide poisoned and not even know it. Now, where that starts to factor into aviation is that you'll have inefficient combustion that will be going through your muffler, and that muffler will have a crack in it, and that crack will then leak air into the air or leak exhaust into the airplane, and big part of that exhaust is carbon monoxide, and then it starts to accumulate inside of the airplane, and then boom, like next thing you know,
you're dying, and you don't even know it. So one of the first things to note, if you don't have a carbon monoxide detector, is like just note the symptoms, and that's what this slide's for. A headache is going to be the first thing that you get, like right off the bat. You can get dizzy, you can get fatigued, like you want to go to sleep. You can start getting kind of confused. You can't think very well. Your vision will blur. You'll start to feel like you're starting to have a heart attack, if you have like gas pains ever inside of your chest. That's kind of what it'll start to feel like. You might get nauseous, and it'll be hard to breathe because your body is trying to get actual air in, but it's not. It's just getting like mouthfuls of carbon monoxide. So this is like something that's super duper dangerous, you'll when you start working on, especially GA airplanes, there's constant attention being paid to the exhaust system on aircraft because they've had a lot of people die over carbon monoxide poisoning. One of the things that you'll do is every annual you'll take a little carbon monoxide card out of the airplane. You'll put a new one in. They're super cheap, and all they do is they basically change colors. They'll get black if they're exposed to carbon monoxide, so that way they let the pilot and the passengers know, hey, look, there's carbon monoxide present inside of the cabin. You need to do something about it. And so that's the kind of the why behind it. Let's look at carbon monoxide detection and then smoke detection. Okay, so the first type of smoke detector is the light refraction type. So the light refraction type smoke detectors contains a photoelectric cell that detects light refracted by smoke particles. Now, once that smoke starts to refract the light into that cell, it senses enough change in the amount of light in the area it's placed, that it creates an electrical current and sets off a warning light up in the cockpit. Now, this type of smoke detector is referred to as a photoelectrical device. All right. Now, what you're looking at here is the cargo smoke detector inside of a 737. Notice that it has like little bars over it to keep it from getting hit and keep things away from it, so that way it can still detect the smoke as it goes through. So this is a really common one that you'll see out there, and you might end up even having to change it. I don't think I've ever seen one actually go off legitimately. Most of the time that it's like something that's happened to it, or it's broke, or something weird's going on. But yeah, so it's a photo or a light refraction type smoke detector. All right, the other type is a ionization type smoke detector. This is kind of like similar to what's in your house. So some aircraft use these ionization type smoke detectors that generate an alarm signal, both usually horn and indicator, by detecting a change in the ion density due to smoke in the cabin. The system is connected to a 28-volt DC electrical power supplied from the aircraft, and the alarm output and sensor sensitive checks are performed simply by just hitting a test switch on the control panel. Um, these are going to be common in your labs. You'll see videos of guys that are vaping inside of the lab, and it's not setting the smoke alarm off. Is because vape is actually water. It's not actual smoke, and so it's not going to trip those things out. But you go ahead and roll a dice if you and try that if you want to do it. I don't know what happens to somebody whenever they actually smoke in the lab, but it's probably not good. But yeah, so it's the ionization type. Okay, so another type of detection system that you'll come across is a flame detector. This literally is an optical sensor that detects a flame itself, which is it's super cool that it can be done, but smoke typically comes first. You're going to detect the fire sooner with smoke than you will with fire. However, there are certain situations where flame is going to be easier to detect than smoke. Let's say, like if you're in some sort of area where there's a lot of wind churning or whatnot, you're going to see the flame probably before you actually get enough smoke there to detect it. Anyhow, so the way that these work, they're designed to alarm whenever they detect the presence of a prominent specific radiation emission from a hydrocarbon flame. In other words, whenever something catches on fire. There's two types. There's IR and then UV, based on specific emission wavelengths they're designed to detect. So basically, if they are looking for fire from a certain type of system, they're going to use IR. If it's a different type of system, maybe they use UV based on what those systems are made out of or what they're burning or whatnot. IR-based optical flame detectors are used primarily on light turboprop aircraft and helicopter engines. These sensors have proven to be very dependable and economical for those applications. Now, when radiation emitted by the fire crosses the airspace between the fire and the detector, it impinges on the detector's front face window. The window allows a broad spectrum of radiation to pass into the detector where it strikes the sensing device filter. The filter allows only radiation in a tight waveband centered around 4.3 micrometers in the IR band to pass the radiation sensitive surface of the sensing device. The radiation striking the sensing device minutely raises the temperature, causing the small thermoelectric voltages to be generated. Now, these voltages are fed into an amplifier whose output is connected to various analytical electronic processing circuits. The processing electronics are tailored exactly to the time signature of all known hydrocarbon flame sources and ignores false alarm sources, such as incandescent lights and sunlight. Now, alarm sensitivity level is accurately controlled by a digital circuit. So that's a flame detector that you could potentially come across. Similar to a smoke detector, but instead of looking for smoke, it's just looking for fire. All right, and then here's your most common carbon monoxide detector. These things are like $1, and you change them out on airplanes every time you do an annual on it. What will happen is that as carbon monoxide gets exposed to that little orange circle in the middle, you'll you'll start to see it turn black, and as it turns black, you'll know that carbon monoxide is in there. Now, you can have other types of carbon monoxide detectors on aircraft, especially the more sophisticated they get. However, when you look at the vast majority of aircraft that are out there are small GA planes, this is going to be the most common carbon monoxide detector that you're probably going to come across. All right, just so that way we kind of like show you exactly what those could potentially look like. This is a Guardian carbon monoxide detector to kind of just show you the price differences that the little cards that you put in there for $1 could be replaced by this $645 uh, carbon monoxide detector. So it's just not really like the value's not there with them unless you're building system from scratch and you can somehow work the carbon monoxide detector in there uh, at cost or at a much lower cost at least.
All right, now let's just that we understand the types of fire, carbon monoxide. Let's talk about the overheat and fire detection systems and how they work.
Okay, so there's three basic systems that you're going to have whenever you start talking about overheat or fire detection. One's a thermal switch, the other one's a thermal couple, and the other one is a continuous loop. So the first thing that we're going to talk about is the thermal switch. Now, the thermal switch is actually pretty common even outside of aviation. Your dryer, for instance, is going to have something very similar to this in it. Now, the thermal switches are just heat-sensitive units that complete electrical circuits at a certain temperature. It's all that it really boils down to. So you have the switches there on the right-hand side of the schematic. Once they go to ground, they will, or they, once they complete the circuit, they will throw an indicator light, and usually you'll end up having an alarm as well. Really, really, really simple. So let's look at one. Okay, so this is a thermal switch that is used on Honda jets and a couple other aircraft. You notice that like you have like a probe that's stuck out on the end, and then that bracket there, that triangular bracket that has three holes in it. That's because it's going to mount to wherever that probe is going to stick into. So you'll find these on like inlet areas, or maybe even inside of oil reservoirs or whatever. Any place that fire may be likely, that's where they're going to be placed. Okay, so here's a cutaway of what it looks like. You notice there's a low expansion rod and a high expansion rod on that probe. And what that's going to do is that as heat gets applied, there's going to be a differential rate of expansion in those two metals. That's going to create a squeezing action on the low expansion rod and push it onto the diagonal springs that are further to the left on that diagram. That then allows those platinum and iridium contacts to touch, completing a circuit, and then giving a indication in the cockpit. Really, 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 really simple. Probably the simplest one. When you come to like troubleshoot these things, basically what you're going to do is hook up a meter, from the switch to the ground, and then start playing with the calibration screw and see if you can get it to turn on or turn off, and then you try to calibrate it. If you can't get it in the right range, then the switch is bad, because there's not just really a whole lot that you can do to quote maintain a switch like this. It's just simply good or bad at the end. Okay, it's probably one of the more common setups is the thermocouple system. Now, whereas the way that a thermal switch operated is as two different metals expanded at different rates, it completed a circuit by pushing together two switches. The thermocouple is a lot more sophisticated. What ends up happening with it is you have like two different circuits that will be exposed to heat. Now, those two different circuits and their exposure to heat will create two different voltages that then are compared. Now, what the thermocouple system is looking for is a differential in those two voltages by a significant amount. Now, the advantage that we get with that is that as the engine gradually starts to heat up, then both of those circuits will heat up at the same rate. All right. Now, if it gets to a point where a fire happens, one of those circuits is probably going to be more exposed to the fire than the other one, and you're going to see one jump way up and the other one stay fairly the same, but then kind of start to increase. That then will throw the switch or throw the relay and give us a light or an indicator or what have you. Now, these are pretty common across pretty much all of aviation, and they also get used for more than just fire detection. Because they are so sophisticated, we can get a pretty good idea of what the temperature is inside of an engine or any sort of apparatus on the aircraft by using this system. Okay, here's a pretty standard example of a thermocouple in general aviation. So what happens is, like, whenever you're installing an engine monitoring system on an aircraft, you're going to turn around, you're going to take the exhaust flange coming off of the cylinder, and you're going to drill a hole, and you're going to slide the actual detector in the thermocouple inside of there, and you're going to secure it with that band clamp, right? That the thermocouple then has the two wires for our two differential circuits, and that will go into the wire bundle that goes into the rest of the thermocouple system. Now, what that allows us to do is monitor the engine heat on every single cylinder. So if you end up having six cylinders, like an IO 540, you'll end up having six of these guys attached to the different exhaust flanges, all piped into the engine monitoring system. This is it's not, I wouldn't say new, but it's becoming very, very commonplace with all the glass cockpits. Everybody wants to be able to monitor the engine health and get ahead of any problems before it results in having to do an overhaul. And so these are becoming very, very popular in pretty much all of GA. If you do a Dynon panel install or Garmin install, any of those glass panels, they're going to basically call for something like this, and you'll probably be installing them if that's the route that you go. Inside of commercial aviation, they're all over the place. Thermocouple systems are pretty common in for both fire detection and overheat warning, but also for just environmental monitoring of any particular system. It'll give you heat to a pretty good degree. But yeah, so those are thermocouples. Probably the most famous, I guess, is a good way to say, fire detection system on any commercial aircraft is the continuous loop. Now, there's two types. There's the Finwall system and then the Kitty system. We're going to talk about both. But let's just talk about like the continuous loop detector as a concept. Now, these are almost exclusively used well, especially in large aircraft engines. So anything from, say, your business class aviation all the way up to like your 777s, your A380s, and stuff like that. Anything in between that, they're all going to use continuous loop fire detection systems. Those are fairly common. Now, a continuous loop detector or sensing system permits more complete coverage of a fire hazard area than any spot type temperature detectors, which is big. Like the continuous loop basically is a detector that anywhere that loop is at, it is part of the fire detection system. So you are able to monitor more of the engine with a singular system. Whereas opposed if you had like thermocouples or thermal switches, you'd have to have them all over the place. You'd have a gazillion of them, and so the weight gets high, the complexity gets super high, you end up having a lot of false positives that cause all kinds of problems and drama that you don't need. Whereas a continuous loop detector, it's one system, but it spans the vast area of the engine to allow you to reduce the amount of hardware that you need, reduce complexity, and keep and try to preserve as much simplicity as you possibly can. That's really kind of the big benefit of the continuous loop. Now, the two widely used type continuous systems, like we said before, are the kitty and the fin wall. Now, let's get into the fin wall system. Okay, so the fin wall system uses a single wire. Now that wire is housed in an Inconel tube with a thermally sensitive eutectic salt that's packed around it. Now, what ends up happening is that wire runs over the course of the entire engine. When one spot of the engine gets hot, the resistance in that wire begins to drop. Now there's a signal voltage on either end of that that's trying to complete a circuit, but it can't because the resistance in the wire is too strong for it to get through. But with the increased heat or the resistance lowered, a connection can be made, and that's when you get your alarm. Now, what's cool about this is that, like, let's say you extinguish the fire. Once you extinguish the fire, the temperature is going to automatically start dropping, and that's going to allow the resistance to come back into the wire because the heat dropped off, and then it's going to extinguish the light. That's pretty neat. So like, you could be flying along, like, oh, we have an engine fire. We pull the fire handles, bottle discharges, puts the fire out. Then all of a sudden the temperature starts to go down. It's like, oh, now we can see that the fire is out. And so then you can report that to ATC, like you've declared an emergency. Like, hey, look, the fire's out, but we're still coming into land. Blah blah blah. And you can also know that you're not going to catch on fire any more than you already have. You can also wire these so that way, if there's a break in the middle of the fin wall system, then you just the section where the break has happened is the only thing that's really affected. Like the two ends will still continue to detect the fire, and will still work in much the same way, which is pretty awesome when you think about just the redundancy of that. That you could have a fire that could cut the overheat detector like in half, but then only that cut is going to be the part that's affected. The other two ends will still work as intended if it's wired correctly. Now you have to be intentional about that. It's not just all of them, but that is the fin wall system, which is pretty cool. Okay, the other type of system that we could have is the kitty system. Those are just two. The main difference is that there's two wires embedded in an Inconel tube filled with a thermistor core material, as opposed to one like on the fin wall system. Now, same thing as the temperature of the core increases, electrical resistance to the ground decreases. So if you think about that, whenever a fire or an overheat situation is happening, that the resistance to ground is going to decrease fairly rapidly, and then give you a fire indication in the cockpit. Same thing with with the fin wall system. The difference here is that you have a lot more redundancy and a lot more options on the table because the system has a little bit more complexity to it. For instance, the Kitty system can supply nacelle temperature data to the airplane condition monitoring function of the aircraft's in-flight monitoring system, or AIMS. The way it basically does that is it's looking at the resistance to ground in proportion to or the resistance to ground and that ohm reading in proportion to the heat that's being generated on that engine. And so once you kind of know that math, it's pretty easy to decode it. They're like, hey, look, if it's really cold, the resistance is really high, but if it's really really hot, the resistance is really really low, and there's a gradient there. So the hotter it gets, the less resistance that happens, and then that gets routed to your box, whichever box is doing the calculations for you, and then gets displayed in the cockpit as a certain temperature. Pretty simple. Now, the Inconel tubes that are or that shroud the little wire itself, so you notice they kind of sit in a little tray or a tube. Anyways, they're perforated stainless steel tubes that are supported by Teflon impregnated asbestos bushings at intervals.
Now, the shroud protects the sensor from breakage due to the vibration and abrasion against the airplane structure and damage from maintenance activity. So basically, you have those wires there inside of that sheath, and you have these little cushion grabs, and they have a very distinct look. You'll know them when you see them. They're kind of like brown. They almost look like phenolic, but they're not. They're actual these like little asbestos and Teflon. I guess like cushion clamps that hold that thing on there, and you can see them right there in the middle of the system, and you'll see these on large commercial aircraft engines, just like the JT9s, and they're pretty easy to pick out. Now these systems are able to be tested, and that's something that you'll do on every pre-flight. If you're doing avionics pre-flight, at least, you'll go through there and you'll test those systems, make sure that the bells ring and all the good stuff. Now, depending on the aircraft that you're working on, this can look very different on how they get tested. Most of the modern aircraft, there's just you'll go to like maintenance data pages and run a test, and the system basically does all the testing for you. On some of the older aircraft, and I believe even on the 37NGs, there's an actual like button that you'll flip up to test. You can see it in the picture here on the bottom left hand, and that will ring all the bells, turn on all the lights, and make sure that everything's working the way that it's supposed to be. And effectively, what you're doing is you're just grounding all those systems, just like as if there was a fire and there was just like no resistance to ground because it was just in flames. And that's all you're really doing there. But that is one benefit of the little bit more complex systems is that you can do a lot to make sure that you're not getting any kind of false indications. Okay, so another little, I guess, advantage you have on some of the more complex fire detection systems is they can be dual loop systems. So, like, this is one from a 777, kind of like a really high level overview of how a dual loop fire detection system works on that aircraft. So, dual loop systems are two complete basic fire detection systems with their output signals connected so that both must signal to result in a fire warning. So that gives you a lot of advantage. You have like both systems have to indicate a fire for it to actually give you a fire warning. If not, it's going to assume that there's something wrong with one of the two loops. So what ends up happening is that it leverages and logic. So you remember back from our digital logic class that you have to have both conditions met for a certain output. So essentially, what happens is that, like, let's say loop one indicates a fire, the system will automatically interrogate loop two, be like, "Hey man, is there a fire?" And then loop two's like, "I don't see a fire." Well, then they're gonna say, "Well, loop one must have something broken with him because they're like if there was a fire that would set loop one off, loop two would also be going off. So if it's just one of those two systems, then that's it's just not a fire. Now if they both indicate a fire, then obviously there's a fire, and then you get all the master caution warning lights and all that good stuff starts happening. But that is the advantages of a dual loop system. Okay, so there's another type of fire detection system that's out there. I personally have never come across these, but they're pressure type sensor responder systems. Effectively, they're doing the same thing that the Kitty and the Finwall system does, but instead of using electric resistance to accomplish it, what they're doing is they're going to overheat your or the helium that's loaded into these vacuum systems, and then detect as the helium gets hotter and hotter. Then you'll know that there's a fire. Like I said, I haven't seen these out in the wild that I can remember anywhere, and I've worked on a lot of different airplanes, so it's probably fairly rare to come across. Most common are going to be your Finwall and Kitty systems.
All right, so now that we understand that those overheat and fire detection systems, how do we maintain them? What do we have to inspect on them? And what's our jobs as airframe and power plant technicians to these overheat and fire detection warning systems?
Okay, so here we are on the JT9. Now, most of your fire loop tests are going to be consist of the same things. Now,
every single engine is different, every single aircraft is different, and so you'll always follow just whatever task is in the maintenance manual, and it'll tell you exactly how you should go about testing it. But generally speaking, you're going to use a megometer, and you're going to first check between a continuity between the two loops, make sure that they aren't connected already, like that they're not grounded to each other, or they shouldn't be to ground. Then the next thing you're going to do is you're going to take the megometer, you're going to tie off to one of the leads, and then you're going to go to the case that's around it, and you're going to do a voltage test. And then that voltage test is only going to be allowed to drop so much. You should have so many ohms between the sensing loop and the casing that houses it. We'll put up a graph of the allowable temperatures and the corresponding ohms on the engines of the Learjet to kind of give you an idea of what one of those tests could potentially look like. But generally speaking, all your fire loops are going to consist of continuity checks and resistance checks to make sure that the loop is still functioning properly. And when you get to the larger heavy commercial aircraft, you still may do these on some checks, but a lot of times they're going to have a built-in test that you just run from the flight deck during like pre-flight or during some scheduled maintenance, and it'll tell you, hey, look, this is the status of the fire detection system, and it's good or bad or whatever. And then if it fails, then you might actually be popping the cowlings and then running these tests like this to try to like run down the problem, figure out where is it failing at. You can also have on condition situations where there's a fire alarm that goes off, but there was no fire, or you might get a maintenance code that pops up and it says that, hey, look, loop 1 of engine 1 is indicating a fire, but there's no fire, so that means that it's grounded, or the resistance is going bad, or maybe it's just old, and the installation is slowly starting to deteriorate, allowing it to get more connectivity than what it's supposed to have. These are all basic ideas of how you could potentially be maintaining a fire loop. Now, generally speaking, you don't ever want it to bend or break, because keep in mind you have a little wire in there with insulation and then a casing on the outside. If you bend it or you break it or you dent it, you're going to give it false indications, and it could potentially basically ruin that fire loop all total, because it's going to keep on throwing you all kinds of false errors or false positives. Other than that, that's just generally kind of like all there really is to it. It's actually a really simple system. When you look at it for the first time, you're going to get kind of dismayed and be like, oh, this is like really, really complicated. But in all reality, it's not. They're brilliant in the fact that they're so simple, but they're so effective at doing what they're meant to do. What are the different fire extinguishing agents that could be employed in a fire suppression system? There are several different types, and we've gone over them a little bit in general for fire extinguishers. Let's see how they play out on aircraft.
Okay, so we went over this pretty extensively in general. So if you want to go over fire extinguishing agents in depth, go back to our general video and look there. But we're going to give them a real quick overview so that way it's fresh in our minds. So probably the first and probably the oldest of all the fire extinguishing agents is actually CO2. They discharge. It looks like a big cloud. Could potentially even look like snow as it enters in the atmosphere. And the idea is that like you're displacing the oxygen with the fire, causing the fire to extinguish. You'll see these in some aircraft if they're older on like recip engines and stuff. But generally speaking, everybody's kind of moved away from it in the modern era. Okay, powder is another type of fire extinguisher that you'll see. This is actually one that you would potentially use, let's say, like in the Army, or even like at Boeing. We used to launch aircraft, and we'd always had a fire bottle that was there to help put out anything that might get started. Now, generally speaking, you don't want to use any of the dry powders, even though that you'll still see them out there getting wheeled around. Um, because whenever you spray them, it leaves a corrosive residue on the aircraft, and so even if you put out the fire, you might have just condemned the aircraft because now it's going to want to corrode all the time, and it's just a matter of time before that airplane basically is not any good for anything anymore. But you won't see these loaded onto the airplane's fire extinguishing system, which we're trying to get to here in just a second. Probably the oldest, most well-known fire extinguishing agent out there is simply water. Water works by hitting the fire and then lowering the temperature to get below the flame point, flash point, so that way the fire gets extinguished. Not perfect on all substances, so you won't see these used a whole lot around aircraft, simply because if you have like a magnesium fire, some sort of metal fire, this potentially could, at best case, have nothing to do with it, maybe even make it worse. Okay, by far and away, the most common fire extinguishing agent that is out there right now in the wide world of aviation is going to be halon. Now, these are little handheld GA fire extinguishers. However, whenever you start looking at fire bottles and things like that, like we're about to look at, like kind of the systems, the fire extinguishing systems that are installed on larger aircraft, they all use halon for the vast majority of them at the very least. Now, halon is interesting. It's kind of almost kind of controversial. It's been around for about 45 years, and it's actually been banned in some parts of the world. But aviation has been granted an exemption because of its unique operational and fire safety requirements. Like whereas like you could spray things with Special K in a house, it doesn't really matter. But like you spray it on a aircraft, you have a bunch of corrosion problems that you then have to worry about. Halon has been the fire extinguishing agent of choice in civil aviation because it's extremely effective on a per unit weight basis over a wide range of aircrafts, meaning that like 1 ounce of halon is going to put out a lot more fire than say like 1 ounce of water or CO2 or whatever. So you'll see halon over and over and over again in aviation throughout the years. It's used elsewhere in a lot of different applications, but it's used extensively in aviation. So get comfortable with it.
All right, so fire extinguishing systems vary greatly. We understand now how to detect the fire. What do we do about it whenever there is actually a fire itself? Let's talk about those systems.
All right, so there's four places that you'll generally find fire bottles installed. First, obviously, is the engine compartments. The engines are going to have a fire suppression system because that's the most likely place you're going to have a fire. Then APUs are right behind that because they're effectively just another engine. Then you have the cargo and baggage compartments where the least amount of control that we have on what goes onto an aircraft is. So you're gonna have a high likelihood that you have some sort of fire shenanigan happening in there. And then next is lavatories, because people will smoke or they'll pour something into the trash can that might spontaneously combust with something else that's in there. You have all kinds of possibilities of fire. So those are the four places you're gonna have fire suppression systems installed. Now these all basically are going to work more or less the same way. You're going to have what's called a fire bottles, which you're looking at here. These are two fire bottles from a 737 that are going to be charged with some sort of extinguishing agent. Most likely, it's always going to be halon. It's some variety or variation of halon, probably HCl 125 or maybe 1301 or something like that. Either way, that whatever's in there basically works the same way. They're going to put that halon in there and pressurize it to a super high degree. Now, the reason why it's so high on pressure is because we want this stuff to come out with a force directly onto the fire, so that way, one, it'll kind of snuff it out, but two, we want to get on there as fast as we possibly can. So these fire bottles will always be super highly pressurized. All right, now every one of these fire bottles have discharge valves installed on them. Now, a cartridge that you see out here on the right is also known as a squib. So you hear people talk about blowing squibs or popping squibs or hearing one bust or whatever. That's what they're talking about. Now, these are two types of cartridge disc release techniques are used. Standard release type uses a slug driven by an explosive energy to rupture a segmented closure disc. For high temperature or hermetically sealed units, a direct explosive impact type cartridge is used that applies fragmentation impact to rupture a pre-stressed corrosion resistant steel diaphragm. Now, most containers use conventional metal gasket seals that facilitate the refurbishment following a discharge, meaning that they want to be able to take it off and put a new one on, so that way you don't have to get a whole new fire bottle, because fire bottles are actually kind of difficult to come by in the supply chain for whatever reason. All right, so this is kind of an idea of like how a fire bottle is tied into the aircraft. We're just going to kind of take it. We're going to look at the number one engine container, and then we're just going to kind of take it apart. So first off, you have a relief valve vent. So even though they're super highly pressurized, if something were to happen, if they were to get hot, if there's some kind of like weird chemical reaction that's happening that would cause it to overpressurize, what you don't want it to do is become a bomb in the side of the plane or whatever. And so you give a place where it can vent on its own. Now I've never heard of one venting on its own, so it's probably very very rare, but it could potentially happen. Then on to the right of the relief valve vent on the number one engine container, you have a pressure switch and gauge. So that is going to give a indication to the cockpit of like, hey, look, this is where the pressure on the fire bottle is at, and it will allow them to make a decision on whether or not they want to fly that aircraft based on the level that the fire bottle is at. If it's too low, they can potentially scrub the flight, or you can MEL it and continue to go depending on what your rules are on that particular organization. Then on the bottom you have there's an example of an explosive cartridge. So that's your squib. That squib is also on the right hand side, and you notice that they're all tied in, so that way they can go to the number one or the number two engine, allowing a level of redundancy to that. In between the engine and the squib is going to be a double check T valve that allows for the halon to go one way, but not to turn around and let anything go back up into the fire bottle itself. Pretty standard when you're looking at fluid systems or gas systems like that, to keep everything going in just one direction. So really, you look at it, it's not that complicated or not that fancy. It's pretty simple. If there is a fire, you're going to look up and then you're going to hit a button in the cockpit that's going to command the squib to fire. When that squib fires, all that pressure's got to go somewhere, and it's going to go right to where the fire is at. So this is in the cockpit. On the overhead panel, you notice that you'll have fire bottle switches for engine 1, engine 2, engine 3, engine 4. So obviously it's a 4-7. And then the APU off to the side. So you would simply, like if you get a fire warning, you would lift up the little guard that covers that switch, and then press the switch, and that'll fire the squib. On a 3.7, it looks a little bit different. So if you remember this earlier from an old 737, you're going to end up, those lights that you're seeing there are actually handles. You'll pull that handle up and you'll turn it, and that'll discharge the fire bottle. It's no different than the 47's switches that we just looked at. They do the same thing. It's just the action of it is slightly different. On this one, you're gonna just simply you see the light. You're already looking there. You reach down there, grab it, pull up, and twist, and then that fires the fire bottle. Now that goes to without saying, is that you don't want to accidentally ever discharge a fire bottle, because it is a complete mess if that happens. So whenever you are testing these, don't pull up on them and don't twist on them unless you're expressly told to by the maintenance manual.
All right, now that we understand that system, let's talk about the maintenance requirements that usually come with the fire detection systems.
Now, every single fire detection system is going to be a little bit unique, a little bit different, but they're going to have the same kind of couple elements in play. Now, this is the Lear kind of overview of their fire suppression system on that aircraft, and we're going to just kind of talk through the couple of things that we're going to end up having to do to maintain it. First off is we're simply just going to check the pressure on the fire bottles. You see the two fire bottles there are they're both in the aft avionics bay. They're about the size of maybe like a large like honeydew melon, and they're very easy to see. And they both have board on tube uh, gauges on it that tells you where the fire where the pressure in the bottle is at. All right, so you can see from this picture here that the fire bottle is getting a little bit on the low side. It should be closer to 10 psi or whatever. That's what in the hundreds, so 1,000 psi as opposed to 500. So that the first thing you're going to simply do is just like look and see where it's at, and then look see what's allowable, and then make a determination of how you go from there. All right, the next step is you're going to make sure that the system works itself. So what you'll do is you'll disconnect the fire bottle from the rest of the aircraft, electrically at least, and you will use a jumper cable to give a false indication that the fire bottle has discharged, and see if that light comes on there. You'll also work it the other way, where you'll put a multimeter on there and then action the fire bottle discharge button up in the cockpit and see if it actually grounds the meter out, and you get a ring on it. But that's basically what you're doing. This is a pretty simple one. Like I said, most of your heavy commercial aircraft, they're going to turn around and they're going to do these electrically. You could end up being on some older aircraft where you have to do these things, but the bigger, more complex aircraft are going to take a lot more time and have a lot more steps to it. The Lear is actually pretty straightforward, pretty simple to do.